KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss some example problems. Between those, one example problem is based on the calculation of work done, and then we are going to discuss about kinetic energy. Afterwards, we are going to discuss about one example problem based on the kinetic energy, and then we are going to discuss work done by a variable force. Work done by a variable force, right? Okay. So before going to start the first example problem in this class, that is example 6.3. Once if you look at the previous class, there we discussed about work and types of work done, types of work, right? So work is said to be done when a body displaced along the direction of applied force. It is the basic point, but if you are going to define the work in a complete manner, we have to say that the work done by the force is defined to be the product of component of the force in the direction of the displacement and the magnitude of this displacement. I will repeat once again. The work done by the force is defined to be the product of component of the force in the direction of the displacement and the magnitude of this displacement, right? So mathematically you can write W is equal to F cos theta into D, that is equal to F dot D, that is F dot D means F bar dot D bar, F bar dot D bar, okay, right. Afterwards we also discussed work is of three types, no work done and positive work and negative work. So work done depends upon three things. One is magnitude of force, another one is magnitude of displacement, and then angle between the force and displacement. You can also say that the direction of force and the direction of displacement, right? So work done depends upon magnitude of force, magnitude of displacement and direction of force and displacement, right? Okay. Then if you go for types of work done, if your body displaced along the direction of applied force so that theta is equal to 0, then work done is said to be positive. If your body displaced perpendicular to the direction of applied force, then theta is equal to 90, then according to the formula W is equal to Fs cos theta or Fd cos theta, work done will be 0 because cos 90 is 0, right? Similarly, if you go for another case, that is the last case where the work done is 0 or no work is said to be done, either the magnitude of force is 0 or the magnitude of displacement is 0 or the angle between force and displacement is 90. Force and displacement is 90, right? So there you can say that the work done is 0, right? I will repeat once again. In the first, I am talking about three types of work. First one is positive work. When your body displaced along the direction of applied force, the work done is said to be positive. Theta is equal to 0, cos 0 is equal to 1. In the second case, if the angle between force and displacement is 90 or if magnitude of force is 0 or over or magnitude of displacement is 0. In these three cases, in these three situations, the work done is said to be 0 or no work is said to be done. Otherwise, if your body displaced opposite to the direction of displacement, if your body displaced opposite to the direction of displacement, okay, then you can say that because theta is equal to 180 degrees, no, cos 180 is equal to minus 1. So when cos 180 is equal to minus 1, W will become negative. So work done is said to be negative, right? So positive work done, 0 work done and negative work done. These three are the different types of work, right? So this and all we discussed in our previous class. But in continuation to that, we are going to discuss one example problem here. That is what a cyclist comes to a skidding stop. A cyclist comes to a skidding stop in 10 meters, full stop. During this process, the force on the cycle due to the road is 200 newtons and is directly opposed to the motion. This is the situation they have given. What is the situation, ma? A cyclist comes to a skidding stop in 10 meters, full stop. During this process, the force on the cycle due to the road is 200 newtons and is directly opposed to the motion. Now, we need to find how much work does the road do on the cycle. How much work does the road do on the cycle? Next, B is how much work does the cycle do on the road? How much work does the cycle do on the road? So these two things we have to find. What are the two things? One is how much work does the road do on the cycle, and another one is how much work does the cycle do on the road based on the given information. One is the distance travelled by a cycle before coming to stop, and then the force on the cycle due to the road is 200 newtons. Based on these two things, we have to find the two things what they are asking, right? First case, solution. First A, to calculate the work done on the cycle by the road, to calculate the work done on the cycle by the road, WR, R means road ma. So work done due to the road is equal to, what is the formula? FD cos theta, no? The formula is FD cos theta. Before writing this, that is what the formula to calculate work done, we also need to remember work done on the cycle by the road is nothing but work done by the frictional force on the cycle due to the road. So I will repeat once again. Work done on the cycle by the road means what? So what type of force the road is exerting? So it is a frictional force. So you have to calculate work done by the frictional force on the cycle. Work done by the frictional force on the cycle. Okay, that is right. So that is WR is equal to FD cos theta. FD cos theta, right? So there, and one more important point I want to say here. What is the angle between frictional force and displacement of the cycle? Displacement of the cycle. It will be 180 degrees. It will be 180 degrees. So that 200 into 10 into cos pi. 200 into 10 into cos pi is equal to minus 2000 joules. Minus, because cos 180 is minus 1 no. So what will happen? Minus 2000 joules. So if you observe carefully, here the work done is negative. The work done is negative, right? So what does it mean? The negative work that brings the cycle to a halt in accordance with kinetic energy, work energy theorem, right? Work kinetic energy theorem or work energy theorem, right? So the negative work brings the cycle to halt according to work energy theorem. Okay, ma? Right. Next. So here, if you observe carefully, so it is the negative work. So if you calculate the work done on the cycle by the road, according to the situation, according to the given situation, the work done came negative. In our previous class we discussed, no. So in sometimes the work is positive, sometimes it is negative, sometimes it is 0 also, right? Okay. Now we are going to discuss next one, that is B. See here. How much work does the cycle do on the road? How much work does the cycle do on the road, right? Okay, see this. From Newton's third law, an equal and opposite force acts on the road. From Newton's third law, what is Newton's third law? For every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction, right? So from Newton's third law, an equal and opposite force acts on the road due to the cycle. Already in the question they have given the force on the cycle due to the road is 200 newtons. So automatically Newton's third law, its magnitude. So the magnitude here, right? So the action is equal to reaction in magnitude. So that its magnitude is also 200 newtons. But the main point is here, the road undergoes no displacement. Am I right? Road is not displacing from one point to another point. But he is asking to find work does the cycle do on the road. So here, if you want to calculate the work done is equal to force and displacement and cos theta. The product of that is what, as simple as such, FD cos theta, right? Here D of the road is 0. Displacement of the road is 0. So that what is the work done? 0. I already told you in our previous class, if the magnitude of displacement is 0 or the magnitude of force is 0 or the angle between force and displacement is 90. In all these cases, in all these situations, the work done will be 0. So no work is said to be done. No work is said to be done, right? So here work done by the cycle on the road is 0, right? One more important point here we have to observe. The point is, right, according to Newton's third law, right, here in this example, according to Newton's third law, the force on a body capital A exerted by the body capital B is always equal and opposite to that on B by A. So it is Newton's third law. There are two bodies, A and B, right? So here also you can take it as no problem. So one is A means another one is B. So here according to Newton's third law, the force on a body capital A exerted by the body B is always equal and opposite to that on B by A. It's okay, it is correct. It is Newton's third law. But work done on A by B is not necessarily equal and opposite to the work done on B by A. Please notice this point. Work done on A by B is not necessarily equal and opposite to the work done on B by A, right? So force is equal and opposite, but work done is not necessary. Okay, right? Next, right? Example problem over. Now we are going to discuss the concept kinetic energy. Kinetic energy, right? So what is meant by kinetic energy? The energy possessed by a body due to its virtual motion. The energy possessed by a body due to its virtual motion is simply said to be kinetic energy. Okay, see here. If an object of mass small m, has velocity v, its kinetic energy k. Just these are the notations, usual notations. Mass means small m we are using, velocity means v, kinetic energy means k. Then k is equal to of m into v dot v, because both are velocity, no? Velocity is a vector quantity, no? Right? So v into v. Suppose if it is speed, no problem, because speed is a scalar quantity. So that finally you can write, because kinetic energy is a scalar quantity. Energy is a scalar quantity, so kinetic energy is also a scalar quantity. Here that is equal to half mv square. Half mv square is a formula for kinetic energy. 1 by 2 into mass into square of the speed. Otherwise, square of the magnitude of velocity. Next, kinetic energy is a scalar quantity. Next, the kinetic energy of an object is a measure of work. The kinetic energy of an object is a measure of work an object can do by the virtue of its motion. By the virtue of its motion, right? So, for example, I told many times, right, we should not throw chalk piece on others. Why? Because when the chalk piece is at rest, its kinetic energy is 0. But when you are throwing a piece of chalk towards another student, towards another boy, so when you are throwing means you are giving some, you are applying some force, so that some certain amount of work will done, so that work will be converted in the form of kinetic energy of the chalk piece. So when the chalk piece is moving means it is like a moving bullet sometimes, right? So when this chalk piece having greater amount of kinetic energy will hit the eye of the opposite student or another student means definitely there will be a chance for the damage of eye. You know that it is very sensitive, right? So because of the sensitive part of the eye enable us to see the entire world, right? So that's why we should not throw the chalk piece in our classrooms. Okay, right. Now we are going to see some of the examples. Same like chalk piece example what I told. Here we are going to see some of the examples of where how much kinetic energy is present. Right? See here. So car, which is the general life example. So the mass of the car is approximately 2000 kg generally, and speed is 25 meters per second. The kinetic energy is 6.3 into 10 to the power of 5 joules, right? So when a car of mass 2000 kg is moving with 25 meters per second speed, then the kinetic energy of the car is 6.3 into 10 to the power of 5. So I can say that right, almost it is what 63 into 10 power 4. 63 into 10 power 4. That much amount of kinetic energy has. Similarly, I am going for another example. It is what running athlete. Running athlete. So generally you take a mass as 70 kg and speed is just 10 meters per second, right? So when an athlete of mass 70 kg is running with 10 meters per second speed means the kinetic energy possessed by him is 3.5 into 10 power 3. So that you can say that 35 into 10 to the power of 2, right? So 3500 joules of kinetic energy he has. Next, bullet. So the mass of the bullet is like 5 into 10 to the power of minus 2 kg, and the speed of the bullet is 200 meters per second means the kinetic energy possessed by the bullet is 1000 joules. 1000 joules. Next, stone dropped from 10 meters height. You know very well, if you drop a stone onto the head of some other student, there will be a damage. So the blood will come, right? So that's why what I am saying is, if you take the stone and drop it from a height of 10 meters means, and the mass of the stone is 1 kg and speed is 14 meters per second means, so the kinetic energy possessed by the stone will be 100 joules. 100 joules. Okay. Next, raindrop at terminal speed. Raindrop at terminal speed, right? So raindrop, mass of the raindrop is 3.5 into 10 to the power of minus 5, right? 3.5 into 10 to the power of minus 5, that is what, kilogram, and speed is 9 meter per second. Speed is 9 meters per second. Then the kinetic energy will be 1.4 into 10 to the power of minus 3. 1.4 into 10 to the power of minus 3 joules. Next, air molecule. So the mass of the air molecule will be approximately equal to 10 to the power of minus 26 kilogram. So if the speed of the air molecule is 500 meter per second, 500 meter per second, then the kinetic energy will be 10 to the power of minus 21, 10 to the power of minus 21 joule, right? So this is all about, in our daily life we are seeing all these things: car, running athlete, bullet, stone dropped from 10 meters height, raindrop at terminal speed, air molecule. So in all these cases, these are the kinetic energy values we have, right? Okay ma, right? And not only these things, the kinetic energy of a fast flowing stream, right? So which helps us to grind popcorn like, okay? Similarly, sailing ships use the kinetic energy of the wind. Sailing ships employ the kinetic energy of the wind, right? So these are all application to daily life from kinetic energy point of view, right? Okay, now we are going to see another example based on the kinetic energy. See here, in a ballistic demonstration, a police officer fires a bullet of mass 50 grams, right? Mass 50 grams with a speed of 200 meters per second, on soft plywood of thickness 2 centimeters. Full stop. The bullet emerges with only 10% of its initial kinetic energy. Full stop. What is the emergent speed of the bullet? That we have to find. Okay, right? So first they have given mass of the bullet and speed of the bullet, right? And the thickness of the plywood also given as 2 centimeters, right? The bullet emerges with only 10% of its initial kinetic energy. So he has given final kinetic energy also. Final kinetic energy given means, if you find the initial kinetic energy, from there it is 10%, right? Okay, how to find initial kinetic energy? Simple formula of mv square. So 1 by 2 into 50 into v square, no, 200 into 200. It is 50 grams ma, so you have to convert into kilograms. 50 grams this is, we have to convert into kilograms, right? So if you find the initial kinetic energy, that is what, 1 by 2 into 50 into 10 power minus 3 into 200 into 200, then you will get it as 1000 joules. So 1000 joules is the initial kinetic energy of the bullet. But what he is saying, it emerges with 10% of its initial kinetic energy. So initial kinetic energy is 1000 joules, no? So what is the 10% of 1000 joules? 100 joules. So 100 joules is the kinetic energy. 100 joules is the final kinetic energy, right? 100 joules is the final kinetic energy. So here of mv, it is the final kinetic energy, that is equal to 100 joules. But he is asking what is the final speed, otherwise emergent speed, right? So by equating these two, automatically you can find final speed, no? Automatically we can find final speed. What is that? It will be 63.2 meter per second. It will be 63.2 meter per second. Now you compare initial speed and final speed. See this. It is the initial speed 200 meter per second and 63.2 meter per second is the final speed. So will it decreased or increased? Right, decreased or reduced. So the reduced by soft plywood material. Reduced by soft plywood material. But how much percentage reduced? So you can say that the speed is reduced by approximately 68%. Speed of the bullet reduced by speed of the bullet reduced by 68%. Okay, right. Next, work done by variable force. Work done by variable force is a small topic. Already we calculated work done by constant force. Constant force means the magnitude of the force and the direction of the force both are not changing with time, right? So when the force is constant, already we discussed work is equal to force into displacement. That you can also write like this, delta W is equal to f of x into dx. It is the formula for work done by constant force. Work done by constant force. But generally in our daily life we came across with variable force also. Variable force means either the magnitude of force or the direction of force or both. The force is said to be variable if the magnitude or direction or both of the force changing with time. Changing with time, right? You see this picture. It is what initial. It is what final position. Initial position and final position, right? Suppose for example if you took only this part, but here it will be very small, right? The area will be very small. Here you can consider it as a constant force, so that you can use this formula delta W is equal to f of x into dx, right? So area will be area under this curve. This is what, right? So from this graph, it is the force displacement graph. Force, it is the force, it is the displacement. So from this force displacement graph, if you find area under the curve, you will get as work. So that you can write it as f of x into dx. But when the force is variable, see the next picture. When the force is variable, according to this picture, when the force is variable, then you have to add up the total area under the curve, right? So the summation symbol you have to use to add up the area of every part which covered under the curve, so that we can write W is approximately equal to summation xi to xf f of x dx. You can apply limit also. As delta x tends to 0, W is equal to limit delta x tends to 0 summation xi xf f of x dx. This is the formula to calculate work under the variable force. That summation and this and all you can replace with the integration xi to xf f of x into dx. So the formula to calculate work done due to the variable force is equal to integration xi to xf f of x dx. F of x dx, right? So this is the formula. So here we are using integration to calculate the amount of work done due to variable force. Okay, right. So in this class we concentrated to discuss one example problem based on the work formula, and then we discussed what is kinetic energy, along with the discussion about kinetic energy of some of the things what we come across in our daily life. Afterwards we went to discuss one example problem based on the kinetic energy, and then at last we discussed work done by variable force. Okay, so we will continue this topic in the next class with continued concept or continued topic.